The video got cut off for some reason. Zoom just quit. So the video got cut off, and the last thing that I wrote is I wrote down what I said, and at the end of the last part, that if we wait long enough to capture a very, very large number of photons on the screen, we observe the familiar classical bright dark fringe pattern. So notice what happened. I'm using the double slit experiment as an arena for reasoning. I'm using it as a workhorse for reasoning out. We have evidence that photons are particles. On the other hand, we also have evidence that light is made of particles. On the other hand, we also know that light produces interference fringes. So then the natural question is, how can particle-like picture give rise to interference fringes? And one potential idea is that, well, particles of light interact with each other in some complicated way as to produce the interference fringe. We now know that's not the case, because we have been sending one photon at a time, eliminating the possibility for interaction. Yet we still get this kind of a double slit interference. So there's some kind of an interference going on, and it cannot be explained by interactions of classical notion of particles. The second reason why we cannot think of these particles in classical sense is that classically we expect that if you do send particles one at a time, you might at best get this kind of a double bell-shaped curve pattern, and if you're very careful, you're going to get basically two very narrow peaks right at the level of the slits. But that's not what we get. So a trajectory like understanding of particles predicts this. What we get is this. And one more point number 4. That if one of the slits is blocked, the photons also build up a pattern. We actually made a prediction what would happen. We predicted this pattern, and again, that's not the pattern that happens. But take a guess what kind of a pattern we do get. The pattern of accumulation. What kind of a pattern of accumulation we do get? We get the accumulation pattern that now matches the one-slit diffraction pattern. Again, there is some kind of interference going on, and it cannot be written off as interaction between particles. So let me write this down. So this is a screen. This I should use a black color here. And so this is one slit. We cover the other one. And so what we actually get is not a bell-shaped curve, but a bell-shaped curve with fringes. It corresponds to Single slit diffraction. It looks kind of like that. This in a single slit diffraction, the central glob is much more dominant, but there are these additional satellite peaks. They're very important because they show that there is interference. Okay, there is an interference phenomenon taking place. And so what I'm plotting here is I'm plotting particle density versus the y-axis, same as what I've been plotting here, for example. So what does all this mean? I think at this point, it would not be hard for you to accept that these are clearly particle-like entities because they, for one thing, we already have that evidence from photoelectric effect, from Compton scattering and others. And in addition, the double slit experiment actually also shows this particle-like impacts. But they're also not particles in the classical sense of things that follow trajectories. And so the moral of this story is that we have to get away from a trajectory-like view of particle motion. That's point number one. And point number two is that the process is inherently random. In classical physics, in classical mechanics, when we talk about motion of baseballs, comets, planets, stars, there is no randomness. The behavior can be extremely complex. It can be chaotic if there are enough bodies involved. But it's predictable. If you know initial conditions perfectly right, you can predict things. There's not going to be an element of randomness. Here, even if we perform experiment, if we shoot every photon with identical conditions, and we do it carefully to eliminate all this silliness with bad experimentation, particles hitting boundaries and so on, the impacts are still random. We cannot predict where the next photon is going to land. We can only predict its probabilities. Now I discussed that the probability is proportional to the particle density, the accumulation density, and that particle density is the familiar interference pattern. It's proportional to the magnitude of electric field squared for photons. So perhaps the classical notion of a wave is useful. We can use wave theory to predict intensity, square of the magnitude of the electric field. But we will have to reinterpret that intensity as giving probability of where particle lands randomly. Lands randomly, but that random landing is distributed according to some probability, and we can use classical wave theory to predict that probability. And this is a good point to stop. I just want to make one more comment. We're going to wane off from the discussion of photons. Quantum mechanics of photons is a very advanced subject. It's usually done at the graduate level in a course called quantum electrodynamics. It's a subject that marries relativity and quantum mechanics, quite advanced. We used photons in order to bring up all these unusual, nuanced issues about wave-particle duality. What we're doing here is discussing wave-particle duality. Next, well, soon, we're going to discuss electrons. They can be slow electrons, not relativistic electrons. And we will see that electrons, surprisingly, also form interference pattern. Now, that's just wild. Electrons, we think of them as like pebble-like objects that follow trajectories. They also form interference pattern. And again, we will have to come up with some kind of an understanding of electrons that's both wave and particle-like. And so we're going there, and we're just using photons as a stepping stone to get to this idea of a wave being useful for predicting probabilities of where particles end up. And eventually that will lead us to the notion of something called the wave function. And once we embrace this concept of wave function, the rest of the quarter is about learning how to use that wave function. And that's where where real quantum mechanics starts. Okay, thanks for attention, and I will see you tomorrow.